major difference between their rotation field and ours. Rotation under arrow. It's the reverse rotation, right? And notice in the function they give, ours was y comma negative x. Theirs is negative y comma x. Right? So one interesting thing to see here, if I just look at, let's take out this factor that makes it a unit vector. Just look at this. What's the slope at every input point? What's the slope of the vector? So if you guys get this.
1, 1.
Can't say that. So the slope, of course, is y over x, because these are standard positions, so it's going to be y minus 0, x minus 0. So it's going to be the y piece over the x piece. So the slope at any point is going to be negative x over y.
Okay.
Cool? Sort of, maybe. Okay, so one thing you can always look at is the slope of a given problem. Okay. Now, the thing here is the slope doesn't really tell me necessarily the direction that it's facing. It actually just tells me the slope of the line. Because vectors don't care about what's parallel to something could be pointing in the other direction. But it at least tells me what direction, what angle it's kind of situated at. Okay, sort of. So they actually have the same slope, it's just that that one's pointing in that direction, the other one's pointing that against it. Okay. How about it so far? Not too bad. Okay. So that one is just rotating the other way around because they put the negative in the other side. So for example, here at the point 2, 2, it's going to be negative 2, comma 2. So it's going to be pointing in the direction of negative 2, 2, so that's why it's pointing up. It's got to be pointing in the direction of negative 2, 2. So it should be pointing up like that. Nice 45-degree angle. I love it. Okay. Not too bad. Good. Here's the example I was talking about earlier. And before I put this up here, let me ask you guys what you think about this. Let me see. And then I'll come back and do that. That's right. Where'd you go? Here you go. Now, just looking at this, what's kind of constrained here? So this is f of x and y. X can be anything it wants to be. Yeah, it's going to be straight lines.
Zero slope.
Slope is 0, so they got to be parallel to the x-axis. So far, so good. So it does sound like that setup I had earlier with the blood flow through a vessel. Okay. And notice something interesting about this. Y has to be between.
Yeah.
Not y, but what am I trying to say here? If I try to put in there, what am I trying to say? Let me put this up here.
You're trying to make it equal to 0, so
exactly.
y can't equal 1.
Actually, I have to constrain this myself. I have to constrain this at y equal to plus or minus 1. What's true about this?
It goes nowhere.
0 and 0.
It's not undefined. It's just a 0 vector there, right? So that corresponds to being right on the wall of the blood vessel. And obviously, if you're on the wall, you're not going anywhere. Basically, you're the wall, so you're not going anywhere. Hopefully, you could go beyond that, but I have to define. So it, like at y equals 2, this would still work. So in order for it to be a blood vessel, I actually have to set up, and I think they do this in the book. Yes. You have to tell yourself, or you have to tell people that to make sure it actually becomes this. So that's what they were missing up here. That's what was throwing me off a little bit. But just to make it defined to be in there, because y can still be greater than 1, who cares? But I have to define it to be that way just to stay on my blood vessel. Hopefully no blood is flowing outside your arteries. Okay.
The y equals 2. Or the y equals 2.
Oh, if y equals 2, then this still works. Then mathematically doesn't care. So I got to set that up to make sure that I stay in the blood vessel physically. The math says, hey, cool, I got an answer. And math does that a lot to us. Hey, you build this thing with a -7 width, you're fine. And then we go, well, I can't do that math. Thanks.
Y equals 2 would be bad.
In this case, y equals 2 if there was blood flowing there. That's outside my vessel, that's not good. So just to show you, how did you see that the slope was 0, of course? Because it's y over x, so it's going to be 0, right? Unless this goes to 0 right at the outside. The funny thing is, the slope tells me sort of the angle that it sits at, and it could be pointing in either direction. But at the point y equals 1, this is the vector 0 anyway. I don't care which way. Infinite slope, but you have 0 length. Who cares? Okay, maybe. And obviously this does not depend on x, it only depends on y. Cool. So you can, when you're given something like this, before you even start plugging points in, you can stand back and tell a few things about it right off the bat. You can see, okay, the slope is 0. You can see that, what else can you see? They'd have to give me this for this problem, so I can see that at the point 1, something interesting happens, it becomes a 0 vector. You can tell a lot of things before you have to go and try to start graphing this thing out. So obviously, like we were saying earlier, these are bigger towards the middle, smaller as you get to the outside. And there's something called flow curves, which is where you just say, screw the length of the little arrows. Let me just do a bunch of representative, that's the blue lines. So that's basically showing the flow of blood. Has nothing to do with the speed it's moving or any of that. It's just showing the flow of blood, what direction. So for that rotation field, if I just saw the flow curves, that's what they look like. Notice that they put the arrows to make sure that people understand it's rotating in that direction. But that's just getting straight to the point. This is if you care about how quickly the wind is blowing, and you might sometimes be interested in that. Right? So sometimes that's the better way to do it. Okay, so a couple quick words about that was nice. I don't know classical music all that well, but could have been Mozart. I don't know. So really quick, recall this example. Another way to write this is, in this format, I could just write this as R. And that's why we call it a radial field, because these point along the radius. If I were to divide it by the length, then what's special about it? Like we saw earlier. Now they're all unit vectors. So I can divide it by any power that I want to here, r cubed, whatever. Something very interesting happens when this p is cubed. Let me break this out a little bit for us. Here's the length. Not the length. Here's the direction. Here's the length is the rest. So this gives me this is the unit vector that tells me the direction is going in. And what's left over is this. Right? If I factor out 1 magnitude of r, what's left is p minus 1. Cool. Is that cool? Yeah. Can I do that? Yeah, you can do that all you want to. But so here I've taken out the unit vector. That's going to tell me the direction it's moving in. And this is the leftover magnitude. And even if you haven't taken physics, you can appreciate this. But those of you who have taken physics, do you remember what the force of gravity?
9.807 times.
No. The full force of gravity between two bodies. Have you guys thought about that?
Inverse square.
Yeah, inverse square law. So you see a lot of inverse square laws in physics in reality because, for example, the intensity of light. If you have a light source and it goes out from the light, of course, if you move r away, it's got to cover the inside of a sphere that's related to r squared. So as you move further and further away, the same intensity of light has to cover r squared worth of a little box. So that's why the intensity drops off as the square of the magnitude, as the square of the distance away. Same thing happens to gravity. Gravity is really strong, but it's long acting, but it's not very strong, is the idea. Right. Okay. Acts over great distances. That's what I'm trying to say there. So that would be related to P equal to what? Inverse square law. P would equal 3. I love it, because you need to have 3 minus 1, so you have to have that thing squared at the end in order for this to make sense. Cool. For P equal to 3. It comes out to an inverse square law. Because this, again, is just the direction. Unit vector showing the direction that it's moving in. Okay. All right, all right. Oh, let's take... Yeah, let's do this here. So let's look back at the gradient real quick. We were talking about earlier that the gradient should be an example of a vector field. And the vector field you create, so let's say we have a function, and of course we've got to get all funky with it. Let's say we have a function phi, or phi. Function, let's say it's xy, xyz. Works in 2 dimensions, but 3 as well, so we might as well just start with 3. The minute you do this to it, can somebody tell me what that would be? What is that? What's the answer to that?
Partial of x, partial of y, partial of z.
So that is a vector defined at every point, so it is officially a vector field. And in fact, we call it, amazingly enough, through the creative juices of all mathematicians, we decided to call this a gradient field. Wow. So this is a vector field, officially. At any point, x, y, z, it comes out with a vector, but we call it a gradient field. Now, if you plan on going any further in mathematics, you have very often what's called, and I see a lot of you guys kind of laugh at you. Hopefully, my class isn't what turns you off to it. This year is called a potential function. So you have, in a lot of different math courses, you have things called generating functions and things. They're functions that are sitting there. They exist on their own. They're little functions, but if you do something to it, it creates this other thing that might have physical properties and so forth. So this is a potential function that becomes this gradient field when you act on it with the gradient. So a potential function goes with its gradient field. I love it. So not every vector field, obviously, can be traced back to a potential function, but a lot of them can. Let me say that again. If I give you a vector field, it's possible to think, what would this have to have been for this to be the answer, for this to be what he's given me? Not an easy question to answer sometimes, and thankfully we're not going to answer the question. Okay. So a real quick example of a gradient field. Here. Straight from the homework. This is on page 969. Number 27 looks pretty. So x and y are both between negative pi and pi. So try to write what the gradient field would look like for this. What would the gradient field be for this? Don't say it out loud. Not yet. So what do we get?
Cosine.
Cosine X, sine Y.
Sine.
Yep. And then you could do, you know, what's the magnitude of it? I could ask you to graph some representative curves of this. Well, what do you think is going to be true about this? Let me just ask you. The level curves of this, which would be like z, let's just say it's a constant, c equal to sine x sine y. And you have to think about it for a minute how to try to graph this thing. But you can try to solve for y. You're going to have like c over sine x, inverse sine of all that. You semi with me? So it's doable. You could actually kind of try to graph some. But what should be true about the level curves you get here? Let's see B4, let's see B7, let's see B whatever the hell. And of course, can't be all of that, can it? Because these are going to be from -1 to 1. And these, if you try to graph some representative vector fields here, what should be true about the level curves of this and the vectors you get from this?
It'd be perpendicular.
Exactly. We know that. The gradient, of course, is perpendicular everywhere to the level curves of the function, right? So all these, so if you graph a level curve and it looks like this, then at this point, the vector field should maybe go that way. It's got to be everywhere perpendicular. Hello. So very often, instead of graphing the vector field, they actually graph the level curves, which gives you an idea about, you have to use your imagination, that they kind of define what's called equipotential curves. And what does that mean? I mean, everywhere on that curve, the fact that it's a level curve, what's got to be true for this everywhere on that curve? What's true on a level curve? What do you do with this? You set it equal to a constant, right? So everywhere on that curve, phi has the same value. And what was the name of this thing again? Not the Greek name, but the definition, the term? Potential function. So that's why we call this equipotential curves, because it's everywhere the potential is the same. Yes, sir?
You said they all have the same values. Is that the same way of saying as they all have the same magnitude, each vector?
I want to be real careful. I've got a function here, and that's what I'm talking about right now. The function has the same output all along this curve. Right? This, by the way, doesn't necessarily go with this, but it's just an example. Everywhere on the curve has the same value, same output. That's how you make level curves, right? You set them to the same output. So everywhere on that, the potential has the same value. It's the equal potential everywhere. So then we just call it equipotential curves. In 3 dimensions, we would call it an equipotential surface. And we've seen that kind of thing also. The gradient should be everywhere orthogonal to a surface if I'm in that many variables. Okay, so same idea, that equipotential. Some of you guys who've taken physics or who currently are taking physics, this sounds very interesting. Possibly.
Yeah, the fields.
Yep. Fields and equipotential areas. Okay. So the math in this 14.1 is not too difficult. Normally what people have trouble with is really trying to give a good plot, a representative plot of a vector field. That's what's going to be possibly most difficult. Even that's not that bad, as long as you remember any given point, you just draw the vector like you would have from the origin. And you don't have to do a bunch of them, you just have to do a representative amount to give the idea of what it looks like. So a little tiny bit of a preview of 14.2. And 14.2 is interesting because we've done, we've worked with these 3-dimensional surfaces along some constraints. So I'm only allowed to use inputs from like a circle or something, right? We've done stuff like that before. It's the whole thing with Lagrange multipliers. So what we're going to do now is, what if you want to try to integrate, but not everywhere, only over a certain curve? So if I had of course, I always imagine a good question there is, why the hell would you want to do that? Say I've got this here, and I want to just integrate over this. So it kind of goes up to there. So I want to integrate just over that. Or I want to integrate over, this is my go-to image here, obviously. I've got some line, and I want to integrate over that line, so it's going to have this little, what's called a curtain that's over that. How are we doing so far? So there's a better picture, obviously, in the book on page 971 of this idea. Get back to it. Here we go. No. All right, here's my whole surface. And there's the line, there's my constraint. I'm only allowed to move along those, I'm only allowed to use those inputs. So you can see it's the curtain. It's truly just got 2 dimensions on it, in a way. That's the part that's interesting. Let me take that surface away so we can just see this curtain. So in one way it is only 2-dimensional, like a sheet would be 2-dimensional, even though if I fold it, you could argue, well, now it's 3-dimensional, but actually it's still 2-dimensional. Every point on there can only move on that surface, right? Do you understand what I'm trying to say? So if I have a surface up here, and I want to, and this, the bottom of the sheet is my constraint line, and I want to know the area of that sheet. It doesn't end up being that difficult, but it sounds like it should be hard because it's squiggly, right? What the hell would dx and dy and all that shit be? You with me? And it's not as hard as bringing in trig functions and all that, thank God. All I really need to help me is the arc length as I move along this. So we have, we've done stuff semi like this before. We're going to use a lot of the same math constructs as we used before to do this. The integral ends up being remarkably easy, but it sounds like that would be freaking difficult. Just to pick out that piece of the whole surface, right? But it's very simple, as long as I'm able to, I'm wrapping it up here, so. This is not the best picture in the world. But you can see this would be the beginnings of a Riemann sum. Don't worry, we're not going to, by this point you should realize I say Riemann summit, and then here's the answer. But I build the lengths based on the arc length. So it still does follow that line. We just got to figure out, what if I don't have the arc length? How am I going to get that from what I needed? And we used the radius before to help us, because the radius to here and the radius to there, r of t. If I take the difference, I end up with the arc length in there. Basically, especially when I take it, infinitesimally small steps. So the integral ends up being remarkably simple, and I've got a very step-by-step procedure for doing these types of what's called, they call it, unfortunately, line integrals. Of course, my line can be wavy, so they should call them curve integrals. Okay, that's fine.
But this is not related to the vector value that we don't have.